Good morning, everyone. Welcome to class. Very nice to meet you again. Today, I'm going to talk about a value-based TNN agent. That is the main subject of the class today. In reinforcement learning, we have agent that will make a decision, and TNN will represent agent. It is combining a deep neural network and reinforcement learning. Next Wednesday, I'm gonna talk about value-based TNN agent. Before to start a value-based TNN agent, let us review reinforcement learning. Because this concept is very complicated concept, it is good to revisit the basic concept of reinforcement learning. Then we will be quickly move into the value-based TNN agent today. In reinforcement learning, we have agent who is making action. And we have an environment. For example, for the game of Go, we have rules and 19 by 19 grid array. If agent make an action, they will receive return reward, and their state will be moved into next state as t+1. And they will keep iteration of action, reward, and state transition. They will gather experiences. By applying those experiences, this agent will become smarter and smarter. In our class, we have two approaches. One is to represent agent using table. It is usually a very small size problem. If the problem is very complicated, then this agent can be represented by deep neural network. That is very core technologies being used in this class. This DNN include CNN, LSTM, transformer learning, and that kind of learning method.
Recording in progress.
And then, in order to find the best decision using this reinforcement learning, we have a requirement that is called Markov decision process. When you are designing this agent, action, environment, reward, and state, it has to meet the requirement of Markov decision process. Requirement of Markov decision process is that next state probability will be solely depending on current state. We do not know, or we do not need information of previous state. Only current state is enough to make a transition probability to ST+1. And so when you are designing this reinforcement learning for your subject, such as game or financial investment or engineering problem, you have to design state to meet the Markov decision process. Also, you have to design the return. Return could be a winning of your game or profit of your investment or margin of your engineering design. So once you design the return, we can also think about future return. And all the summation of future reward, this is current reward, next reward, and next reward, and it may go up to infinite. And all the summation of future reward is called return. In many cases of reinforcement learning, we want to design or train agents so that they can maximize the return. Sometimes we will be able to calculate return very easily. That is the case of model-based reinforcement learning. That means we know those probability of transitions. But in many cases, we do not know exact probabilities of transition. Then we have to obtain this state value function from the sampling method. So this state value function is definition of expected value of return. Sometimes it can be directly calculated using this known model, but sometimes we can obtain this return, expected return, that is called state value function using sampling method. There are two sampling methods in our class. One is Monte Carlo method, second one is temporal difference method. At the time, Bellman equation was very useful to obtain this state value function. These are the overview of the reinforcement learning. This is another overview of reinforcement learning in this class. Let's assume that you have Monte Carlo process. And if your problem is very small, we can use tabular method. You can write it down as state value function, and you can update it using Bellman equation. One of the three of this Monte Carlo process is model-based Monte Carlo process. In that case, we know the probability of transition. If we have an action A, then we can calculate state value function with the given policy pi. So if you combine this probability, you remember that we had this grid problem at that time. Initially, they had random policy of state transition, 25% up to east, 25% to north, 25% south, 25% to west. In those cases, we know what is the policy and transition probability. Then we can calculate state value function with the given policy pi. That is called prediction. Once you have this state value function, you can update policy. You can get the new state value function. Using this one, we can design new policies, probability of action, and then you can calculate predict the state value function again. So you start from a policy, and then you calculate state value function, and you update policy, and eventually you will reach to optimal state value function and optimal policy. Determining this policy is called control, and upon this policy, if you calculate state value function, that is called prediction. So in the case of model case Markov decision process, you iterate between policy update and the value function update. And eventually you will reach to the optimal policy and optimal state value function. That is the one very easiest part of Markov decision process. Second part, where you have very small size problem and you can still use the tabular method, but the difference between model-based MDP and model-free MDP is that In the case of model-free, we don't know the probability of transition. In the previous case of a model-based case, sometimes we use the random policy or sometimes we choose certain policies. But in this model-free MDP, we don't know what's the transition probability. One method to overcome this situation is to using the Monte Carlo method. In Monte Carlo method, you explore transitions randomly and you go up to the end of episode. If you start grid, at some point, you just go through some episode and up to the end of episode, you will be able to calculate return. Return is the summation of reward at each transition. So you just update state value function that is the form of tabular using this equation. We assume that this term, new return, and the previous state value function, the difference is we assume that is the error term. And this error term is added with ratio to the next value function. By doing this many times, we believe that this value function will become true value. That is the beauty of Monte Carlo method. It needs a lot of computing power, and one requirement is that if you, in the model-free case, if you want to calculate the state value function, if you want to use Monte Carlo method, you have to go to the end of an episode. By doing that, you can calculate return. This new return minus previous value function will be an error term, and that will be added to next updated value function. But there are other cases where episode is not terminating. Usually game will have us at certain state, it will be ended. But in stock investment or some Monte Carlo process environment, it is not terminating, it will go infinitely long. Then they just move one step by, we assume that this is true value. By moving just one step and using Bellman equation, we update state value function. We assume that this is true value, this is going to be error term, and that will be used to update the state value function. Once you know the state value function, based on that, we can make a best action. That is the process of reinforcement learning. And so once again, I said we have two different Monte Carlo process. One is model-based Monte Carlo process, and the other one is model-free Monte Carlo process. And if the size is small, it will be represented by a table. But if the size is large, we have to use the deep neural network. That is the core part of class today. So if I tell you a little bit in advance, this value-based agent, DNN agent, is the class of our work. And this means that it's the model-free, and it's gonna be large size problem. And it will be represented by deep neural network. Deep neural network can produce state value function or action value function. State value function is expected return at state S. Action value function is the expected return at state S if you make an action A. So action is added in this input of neural network. This theta means this is represented by a deep neural network with the parameter theta. So during the training process, theta has to be updated. In CNN, we know the labeled truth value and output of deep neural network. If there is some difference, we are using that difference to make a back propagation. So how are we gonna that? In reinforcement learning, that will be the main contents of class. We will revisit again, but later on, I will show you that in the Monte Carlo method case, that is the case of episode sampling up to the end of episode. And in those cases, this is the return. This is the network output of state value function, and this is the gradient of next output function. And by calculating this, we will add and we will update parameters. Parameter means the weight of deep neural network. If you are using temporal difference method, we're gonna use this updated return minus network output multiplied by gradient of network output. And last, I will talk about Q-learning. So once again, I would like to say our class focus today is talk about this equation number 1, number 2, and number 3. Those are the target of class today. There are another type of network that is called policy-based agent. That in mathematically that is described by pi theta as. This Polish value-based agent will give you the output that is expected value function, but policy-based agent output of the network will give you the probability distribution of states who has the highest return probability. So pi is more likely policy function. This is the value function. That is the difference between DNN agent and value-based agent and a policy-based agent. Don't be pressured too much. On next Wednesday class, we're going to talk about policy-based agent very intensively. In the policy-based agent, so this will be the main focus of our class today, value-based DNN agent, and Wednesday we're gonna talk about the policy-based agent. In policy-based agent, we're gonna, this DNN will give you the probability of state who has the highest expected return. And in this case, we're going to use the target function to make a back propagation, and that is expected return of action A as state S. So we want to maximize this target function, and we will update this policy network to produce the highest target output. And there are two algorithms. One is reinforced. Then we're going to use this equation to update the back propagation. Another method is actor critic, and during this sampling, we're gonna use Monte Carlo method and temporal difference method. And another type of the policy-based network is actor critic, and that will be the also important subject on next Wednesday. So Um, I would like to give you the overview of class or overview of our whole semester. We are going to talk about reinforcement learning, and if the problem is very small, we can use the table method. In table method, there are two methods, model-based case or model-free. In model-free case, we use Monte Carlo method and temporal difference method. But in our class today, we're gonna use the deep neural network to represent agent. There are two different agents. One is the value function agent. Second is policy-based agent. And today I'm going to talk a little bit deeply into the value-based agent. Now, I'd like to talk about the model-free value function evaluation. Value function evaluation is called prediction. And model-free means we do not need to know about the probability of state transition from S to S dash when you make an action A. And in this case, we are using two different methods. One is the Monte Carlo training method. We update, in the case of tabular method, we updated the state value function using this equation. Up to the end of episode, we will obtain this return, and this return is, we believe, that very close to true value. So the difference between the true value and your current state value function, that difference will be error term, and with the ratio alpha, this state value function will be updated. That is the main concept of Monte Carlo training. And alpha could be very small number. Let's assume if alpha is 0.001, if at least you have to have more than 1,000 iterations to keep a 1,000 Monte Carlo episode to update this state value function. Once again, if you once know state value function, you can determine the policy. And by doing this iteration, finally, you can reach to optimal policy. So in order to obtain this return, you have to generate episode. There might be random generation or greedy generation, or there might be many different strategies, but you have to generate this episode, and you have to go to the end of episode to calculate this return. And if the size is very small, you can use a table, but if your problem size very large and complicated, you have to use the agent network. The reason we have to go to the end of episode is because of definition of return. You have to add all the return, expected return, up to the end of episode. So if gamma is 0, then you look at just next return. But if you choose return gamma minus gamma 1, that means you have to go to the end of episode. That means you are putting more emphasis into the future of return, reward. This is very futuristic. This is very short-term decision. Because of the Bellman equation, this return can be rewritten as if you make an action, the next reward, and the next state return. By adding these two terms, you can calculate. So if you apply the temporal difference method, you just obtain this number, you can add it to calculate the return. So basically, Bellman equation is used here again. In the temporal difference method, you also have to generate episode, and you can move one step, and using the Bellman equation you can update this return. This return will be used to update state value function. And we assume that this is more close to the true value, and this is the current output of your table or neural network. That difference is used to update the state value function. And this Monte Carlo temporal difference training also, if the small size, the problem size is very small, you can use table method. If the problem size is very large, you have to use agent network. There are two approaches in the agent network. Agent is represented by DNA networks in reinforcement learning. That is called deep reinforcement learning. So in deep reinforcement learning, agent is described by deep neural network. There are three different types of deep neural network. First one is value-based network agent. Second one is policy-based network agent. In value-based network agent, the output will give us state value function or action value function. Either you have state value function or action value function. Based on that, you can make best policy. But when we are representing these value functions, we put theta on the bottom. That means this network has the network parameter theta, and that is the neural network parameter. And during the backpropagation, this has to be updated. And we usually use the gradient descent method. That was the important subject of deep neural network at the beginning of this semester. We will use that concept to update this value-based network agent. Please remember that this agent is part of reinforcement learning. In reinforcement learning, we have agent, environment, state, action, and reward and return. And this, in reinforcement learning, this agent is represented by deep neural network with the parameter theta. And to make a best decision, you have to update this parameter theta to make best action. And this V pi theta means the value, expected value function with the key policy pi, and this state action function is that expected value when you are at state S, make an action A. For example, if you have a Go game, if you put your next Blackstone here or there, you may have different value. That is this Q pi. And if that is represented by deep neural network, we usually put theta under this Q. Second approach is policy-based network. Policy network pi give you the probability of action A at state S. In Go game, value will give you the expected winning rate, but pi in Go game will give you the probability distribution of winning, who has the best possibility of winning. pi is a more likely probability distribution, and this value-based network give you the value. So there are two different type of network, and personally, I know that this policy-based network agent has the better performance. And sometimes there are intersection area where they are using two agents together. Actor agent used a policy-based network, and critic agent will use the value-based network. This policy network, actor network, and critic network are combined together to serve as network agents. This is third type of neural network agent. This is still overview of our class today and Wednesday. Today, I'm going to talk more about value-based network, and Wednesday, I'm going to talk more about policy-based network and actor-critic network. Actor-critic network will use the both value-based agent and policy-based agent together to make best action. Now, let's focus on value-based DNA agent. Just in the previous slide, I show you that we have value-based agent and policy-based agent, and we have actor-critic agent. So now I'd like to talk about value-based agent. Because this is the deep neural network, it has input, hidden layers, hidden layers, hidden layers, and finally it will have an output. If you are using CNN type of DNA network for the reinforcement learning agent, you will have convolution layer, pooling layer, convolution layer, pooling layer, and fully connected layer at the end. You may use the ReLU function for activation function, and at the end of output you may use the softmax function. Depending on what type of activation function and softmax function being used, we may have different chain rules of backpropagation. So if you put, let's consider a game of Go, it will have a state input of 19 by 19 plus n, and is containing some rules and some informations. That will be the input of a deep neural network. Output, meanwhile, output will be the value function of state or value function of state S if you make an action A. So if you use the value-based CNN agent, you have to determine reward and then return. Return could be winning. If you win, it could be 1. If you lose the game, it may be -1. So that will be used. So if you make a certain action at certain grid point, they will have different return value. And once by comparing network output and GT, by difference, this difference will be used for the backpropagation, forward propagation and backward propagation. By repeating this forward propagation and backward propagation, you can update this theta parameter, network parameter, to make very competitive and very smart. In the case of value-based agent, we will use this loss function. This is mean square error type of loss function. As I said before, these are output of your current network. This will be obtained using Monte Carlo method or temporal difference method. This value will be obtained Monte Carlo method or temporal difference method. And so you will update this network theta to minimize this loss function. So once again, this is the loss function. Loss function is a kind of parabolic, so you want to reach up to the optimal point. So you have to use the minus, you have to use gradient descent. That means you have to update theta with, if the slope is positive, you have to go negative direction. If the slope is minus, you have to move plus direction. That is why we have minus here. So you have to obtain the gradient of this loss function that is defined here, mean square error, and that by calculating this with the multiplication of learning rate alpha, you just update theta. You just update this network. You remember that if this network is represented by LSTM, you have to use the back propagation through time. If you are using the CNN, you have to develop chain rules to update theta. That is the very also difficult part of work, but if you are using Python or PyTorch, you may be able to do that. Computer can do that for you. Now, we have to calculate this gradient, that is the vectorial derivative of loss function with respect to the theta. And this is what it is. Let's see one by one. Because let's look at this one, derivative of x dash minus x squared. If you make a derivative of this function with respect to theta, 2 will come out of here, and x dash x come here, and x has to be differentiable. Then because of minus, minus will come out here, and then finally you have to have dx dt. That is a high school mathematics. Then minus 2 x dash minus x dx d theta. That is exactly here. V true minus V theta, this first term is x dash, and V theta is x. So because of this square term here, that it comes first, because of minus, it will come here. And then finally, you have to make a derivative of state value function with respect to the theta. That is update equation. And that is inserted into this gradient descent equation. And finally, you will have this equation. This is update equation of your network parameter. As I mentioned before, if you want to calculate value-based agent, so agent is represented by deep neural network, so you have to train them. And in this specific case today, I'm going to talk about value-based network. That means we're gonna calculate the value function or state value function. And then output of this value function or state value function will be the DNN output. And DNN has the parameter theta. How are we going to update this state value function? because we will define this loss function with difference of true value and the current output square, and derivative of this loss function will be used. And derivative of loss function is this term. So this is the basic form of mathematical equation to make an theta training. It combines gradient descent method, definition of loss function, mean square error, and by applying these derivative rules of high school, we can obtain this updated equation. That is the very core part of value network training. So once again, this is my lecture style. I'm going to repeat and repeat it again. To make a best action or best decision in our life, reinforcement learning is very useful methodologies. And reinforcement learning is very traditional control theory. Now, in a case where the problem is very complicated, then simple calculation or simple computation may not be enough. Then agent is represented by deep neural network. There are two different types of deep neural network. One is the value-based network. The other one is policy-based network. Today, I'm going to talk about value-based network. Value-based DNN network will give you the output of value function or state action value function. That is expected return when you make certain transition or action. Then you have to train your network. Then let's assume that you have true state value and your output value. That difference is being used to go back propagation. In order to do back propagation, you need to have a derivative of your error function. And by assigning this error function and derivatives, we can obtain this final value function, final update of network parameters. Agent network parameter can be obtained using this equation. If you know your network, it is, let's assume it is CNN or LSTM or transformer learning, you know activation function, soft X function, and so on. So we can calculate this part. And now next question is, how are we going to calculate true value? We will obtain this true value either using Monte Carlo method. If your problem is terminating episode, you can apply Monte Carlo method. If your episode is non-terminating, you can apply temporal difference method. So now our lecture will focus on how are we going to obtain the true value. In Monte Carlo method, to be true, this return, at the end of return in Monte Carlo episode, you will obtain the return. And we assume that return is true value. So this equation, new equation, will be used to update your parameters. You have deep neural network with the network parameter theta, and output input is state, output is, let's assume that VST, and you have to update theta during the back propagation. We're gonna use this equation. So you go up to the end of episode and you obtain the return. At each episode, this return will be inserted into this equation. and use this equation. It will be used to update your network parameter. That is the basic concept of model-free value-based DNN agent. In those cases, one method to obtain return, true value return, is to using the Monte Carlo method. Second approach is temporal difference method. In those cases, we are going to use one-step return update using the temporal difference method and plus Bellman equation. We assume this is the true value. This is one-step sampling and update the return, and this new value will be used to update this network parameter theta. In Monte Carlo simulation, we will go up to the end because of that we will obtain this return, and that will be used to update network parameter. But in Monte Carlo simulation, in temporal difference method, we just move one step, and this we assume this is more closer to the true value, and this error term will be used to update this network parameter, and this is the slope. How fast, how large. This is how large the real value and the difference with real value and the current output. This is more likely slope, how fast the error is. This is the error slope. By multiplying these two, we can efficiently train theta. The reason we have plus here, usually in the gradient descent we have minus here, but the reason we have plus is because during the differentiation, minus term is multiplied to minus and eventually it gives us plus. The last subject I would like to talk today is deep Q learning that was used in Atari game, and it includes action. That means in the previous slide, action is not involved. Expected return as state S. There might be many different actions possible. So more specifically, we can add action. So it is the expected return when you are at state S and action A. So it has more specific on action. So we assume that this is true value. You try many different actions, A1, A2, A3, and each time we may have different state. You try many different study episode, and you choose maximum case, maximum action. You choose maximum action, and that difference, we assume that is true value, and that current network output, that difference is being used to update this network value. That is called deep Q learning. Especially this was became famous because this was used in Atari game, and it was very because you try many different actions. It is multiple computing power. You need multi computing power and multiple episodes, but it can add all the possible actions. And so in value-based network, there are not single method. There might be many different methods. And one deep Q learning is using the Q theta SA function to represent the agent. This is the agent is represented by deep Q learning. It is involved in action and it chooses the best action to give us highest return. This is the summary of our class today. So today I wanted to talk about value-based DNA agent, and it is especially very useful for model-free case, large size, and value. Using this value-based DNA agent, we can make best action. This is the end of our class today. I wanted to give you a more and more overview and large picture of our class and deep reinforcement learning. Thank you for your attention. And coming Wednesday, I will talk about value-based DNA agent. That is also very important and difficult part of reinforcement learning. At the end of Wednesday class, I'm going to talk about AlphaGo, how they use this value-based agent and policy-based agent. Thank you. See you Wednesday.